hard work we've done over the past 3 years has finally, or is coming finally to fruition with this conference and with the report, and hopefully it will plant the seed for forthcoming projects where we can learn and investigate more in depth about this topic of the whys of the gender gap in science. Just maybe one word about myself. I'm a data scientist currently, but my background is in astrophysics and in gravitational physics. So that's where I come from, and my interest in analyzing the publications or bibliographic data came from my prior work as editor of the Central Blood Mass, the bibliographic database of scientific mathematical publications. So our project was named Gender Gap in Science, Technology, Engineering, and Mathematics. This means that from the very beginning we wanted to go over just one particular discipline into the general STEM subjects and include all the possible fields and disciplines within this STEM broad field. But this means also that when we spread our focus, we need to take into account that different disciplines are different from each other. When we started this project 5 years, or the original analysis of the mathematics data 5 years ago, we were very focused on the practices of mathematics. And when the project was formulated to expand to other disciplines, it needs to be remembered and understood that every scientific community has its particularities, and therefore any analysis we do about the gender gap has to take into account that not all STEM fields are born equal. And this is why this talk is going to be focused in what can we learn about the gender gap per discipline. And I'll try to give a bit of light into these different disciplines. Fortunately, though, this project had the big lack of having very interdisciplinary unions as collaborators. So we could, from the very beginning, have input from not only the mathematics community, but applied mathematics and astrophysics and physics and history of science and chemistry and biology through all these unions that are specific to their field. So this, from the very beginning, set our focus into being as broad as possible in disciplines and to study the challenges of each field independently. As how the project was organized, as you all know by now, we had organized the project in these three different blocks. One would be like, maybe if you want a bottom-top approach, so you start asking people, so the global survey of scientists, coming from the information that people give you as scientists to try to make general assumptions. That was task 1, the survey. Then we had the data analysis of publication patterns, the task 2, in which the focus was maybe the other way around, like you have the output in scientific publications as gathered in these particular bibliographic databases, and from that general data, you try to make assumptions about the individuals that are behind. So if you want, these two tasks were a bit complementary to each other. And then we had the database of good practices as a way of compiling specific actions that you can have and you can make to promote the more participation of girls and young women in STEM. In my talk, I will only talk about results from the task 1 and task 2, because it was never the intention of the database of good practices to say things about the specific disciplines. Maybe some anecdotes or some examples come from the examples in the database, but it's mostly from task 1 and task 2 that we can say something about the gender gap in the various disciplines. So I will talk only about the survey and the data analysis of publication patterns. So the methodology, as I said just a minute ago, the methodology to address the difference in the various disciplines from these two parts of the project was different. In the global survey, we rely on the self-disclosed information of the respondents, which is subjective and which is individual, and so it's a survey. Whereas and we enter the different fields of the people by means of the self-disclosed field of study that they name. So in the survey, the disciplines come through the identification with this field, what is your primary field of study. That's how you say you are an astronomer or this is related to mathematics, by self-disclosed information. Whereas in the data analysis of publication patterns, we have to first say which field are we going to study, then we have to identify which is the bibliographic database that we can and won't analyze, and then we choose the field by saying, okay, let's look at biology, so let's find a database for biology. So different approaches again. And how we analyze the data in terms of disciplines is also different in these two tasks. In the global survey, you have all your data, and now you want to say something about mathematics, then you hold out all other variables constant, and then say, okay, then holding everything constant and then looking only at this axis, which is mathematics, what can I say? That's how you restrict your big data to only one dimension, which is the discipline. In the data analysis of publication patterns, because we are doing different analysis of different data sources, we really had to adapt our code and our infrastructure to the different disciplines. So we could not say, okay, now do the same for informatics. No, because we needed to create first the infrastructure for each field. So we cannot replicate one by one in the databases that we've analyzed in task 2. We cannot just change and say exactly the same for other disciplines because the databases are fundamentally different and they have different data. So again, a bit of difference in methodology between the global survey and the task 2. But nevertheless, with all these introductory caveats, let's go into what have we learned about the gender gap for the various disciplines from the global survey. So as I said, the various disciplines in the global survey come from self-disclosed information that is in the field of study. And these are the fields that people could choose from. So when we say various disciplines for the survey, we mean these disciplines. How do we analyze them? Well, we heard yesterday in the talk by Susan that in general, we can say that the survey gives compelling evidence that women and men do not have the same experiences in STEM, and moreover, that the experiences of women are less positive than men. This across all disciplines. But can we say something specific to each of the disciplines? To do that, we need to resort to bivariate analysis that can also be used to explore gender differences in perceptions according to these three different axes that we've seen already: regions, societal development levels, the two talks that we've already heard this morning, and the disciplines, which is what I'm going to say. So restricting all the data to this axis of disciplines brings the results I'm going to highlight next. Let's start with the beginning. The beginning is, when do you decide that you want to go into a STEM field or not? For this, there was this question. What was the period of time in which the respondents chose their primary field? And here, as we've already seen, when it's gray, it means that there is no significant difference between men and women. And when there are colors, it's because there is some significant difference. As we see here, there is gray in astronomy and in physics, pointing to evidence that there is no gender gap in astronomy and physics in what refers to when people choose their field. So in principle, women and men, astronomers and physicists, did not experience any gender gap when they were choosing their field. And if you notice, for these two, the majority, let's say 50% of respondents, made that decision before going to university. So it may be that a factor to promote the removal of gender gap in STEM fields would be to encourage people to make decisions about their future before going to university, before society maybe puts more biases and more constraints into your choices. But this is just a hypothesis. So yeah, regarding this question, there seems not to be a gender gap in astronomy and physics, but there is a gender gap in the other fields, because as we see, for instance, in computer science, there is a difference when they chose their field of study. Now, coming to the quality of relationship with advisor, which may be another very important factor after you've studied your PhD. So how good your relationship is with your, basically the most important person to you during your doctoral studies. We see a lot of gray here. There is no evidence of a gender gap in biology, computer science, history of science, or applied mathematics, meaning that people on those disciplines, they didn't experience a worse relationship, again, it's a perception, with their advisor just by the fact of being a man or a woman. So again, positive things in those fields. That's the thing, that when you say there is no gap in these fields, it's for this question, because we certainly know that there is a gender gap in STEM, in number of participants and so on and so forth. So by looking at these plots and identifying what are the gray areas, we can at least remove some factors that may explain the gap. So we can say, okay, there is a gender gap in astronomy, but that gender gap is not explainable just by the fact that, so when women and men choose their field, because they don't see, you don't see that difference in this plot. The same way you cannot explain the gender gap in computer science by means of the bad relationship with the advisor, because there is no statistical significance that the relationship with the advisor are worse for women than for men. Question?
Yeah. So I don't understand if there is no significant difference. For example, if I read there at applied math, I see that men 93%, women 88%.
Yes, but all these measurements, because the significant difference is that all these numbers are, have an error bar, and the error bar of this number is larger than the difference, so that you cannot say that you can repeat the experiment and the experiment will be different numbers, and the difference between these two experiments will be larger than this difference, therefore is not statistically significant. Which, to calculate that, you need to have this alpha, the false, this coefficient that Susan talked about, plus also the size of the sample. When your size is very small, then a large difference is not statistically significant, because just by one person changing their answer, the whole percentage is completely different. So you also need a certain number of respondents to be able to tell the statistical significance.
What do the colors mean on this?
Gray, again, not significant, and just green is women and men is orange. And then this is because the answer is yes, no. This is just the percentage of people that say, yes, I had so the number is yes. So 88% people said, yes, I have a good relationship with my advisor.
There is another issue here that almost everywhere, 85% had not a problem with their advisor. So this should not be really an issue of explaining the gender gap in general, even if there are some differences between men and women. Because it's only a fraction of the respondent that had a problem, a very small fraction.
Right.
Overall.
Indeed. Again, with the interruptions during doctoral studies, we don't see evidence of gender gap in these fields, astronomy, biology, history of science. However, if we look at regarding the...
Can I ask a question back on the previous one? So it's back to this question of holding things constant versus averaging them out.
Yeah.
I mean, suppose there was a difference between, people who got their doctorates in the 70s and people who got their doctorates in the 2000s. You wouldn't see that difference here. So it seems to me it's not really holding it constant, it's averaging out all the other variables.
So if you want to take the age into account, then you do this multivariate analysis in which you split this data also by this perpendicular axis, which is the age, and then you would have for each of these now, for these blocks, all the ages.
So you're right, so what you've done is averaged out
Yes.
the other variables.
Right. But again, this means that accounting for all ages and for all other variables that are constant, we don't see, so these are the results. So that's when we say this. But again, Rachel and Susan are the ones to explain again what it means to hold the other variables constant. Thank you. The survey, because it's about perceptions, and because not everybody answers to all the questions, I guess, this is also a reason, has some answers that are really not consistent, maybe they are not consistent with each other. No, in principle, astronomers I don't see any difference in women and men astronomers regarding the interruptions during doctoral studies. However, they do report that becoming a parent had an effect in their career progression. But becoming a parent is most likely an interruption of their doctoral studies. So you see, it's sometimes
Not necessarily, it should happen some other time.
yeah, but this is a subset of the reasons for which you may interrupt. So you don't have significant interruptions in your doctoral studies. But the ones that had, because certainly becoming a parent is an interruption in your doctoral studies, at least...
They could have become parents at any other time. Not necessarily during your doctoral studies. I mean,
Right, your career and your doctoral
Yeah,
studies.
it's at
Okay.
any time in your
Yeah.
career that you could have become a career.
Okay, that's true. That's true. Then okay, maybe then there is no
But of course it's
contradiction
about
here.
perception, so
Yeah, but you would see here, okay, astronomy, there is no gender gap in astronomy regarding interruptions. However, there is a gender gap in astronomy regarding the effect of becoming a parent on career progression. See, therefore, it's very difficult to say what is the survey telling us about the gender gap in different disciplines, because it depends on the question that you are asking. Yes?
When you get a question, could you repeat it back?
Yes, yes. So before the thing was that this is any interruption during your doctoral studies, and this is becoming a parent, which doesn't necessarily happen while you are in the doctoral studies. Mark?
So for astronomy, it seems to say that 37% of women that there was a significant impact on becoming a parent.
Yeah.
For biology, for example, it's 27%. Is that difference significant, statistically significant?
Apparently we didn't test. But that's why I said the worst field is astronomy, and in this plot the best field is applied mathematics.
But we don't know whether that.
But we don't know if there is exactly. Finally, we can all agree that there is a gender gap in all disciplines in respect to experience or having the perception of having encountered sexual harassment. And in this case, the worst field is history of science. But I mean, the fact that applied mathematics is 20%, so 20 points less than history of science, must mean that the harassment in applied mathematics is significantly less than history of science. But again, without knowing the effect size, without knowing how many of these people actually, so how many people are in this bar and how many people are in this bar, is also difficult to say whether history of science is intrinsically worse than applied mathematics in what respects to sexual harassment. I don't want my talk completely being like we don't know. It's just I'm saying that everything has to be taken with a grain of salt. This sort of closes the general questions, and you can see more of them in the report. There was, however, so when we designed the task 2, the data analysis of publications, we wanted to see if we could cross-check answers from the survey with the data from the databases. And really, it's very difficult to check, looking at your publications, whether you've had interruptions in your career. This is difficult. So that's why the only question possibly from the survey that we could cross-check with the analysis of bibliographic sources was the one regarding submission to top journals, because in the publication analysis we were looking at top journals. So that's why I'm focusing specifically in this one. For this question, which was how many articles have you submitted to top journals in the past years or in your career? Or no, per year? Sorry, what's the formulation of the question? How many papers, how many papers have you submitted in your career in top journals? The women reported fewer, 5.7 in average, in the last 5 years compared to men. So this is something that we can test, because we have the top journals if you want, and then we can look at how they publish. But first, let's look a little bit more about the results. So these were the mean data, so mean values, 5.7 and 6.3, but this is the histogram of answers. Obviously, it's not true that people come at 10 and then they stop publishing. It's because when you quote the number of papers that you've published, you tend to remember 10, maybe it's 11 or it's 12, but 10, 15, 20, it's like people cluster in their mind how many papers they publish. So if you've published 1, then you remember. But then when you've published 9 or 11, so this is why the histogram has these bumps at these numbers. But then you look at the women, which is on the, if you want, on the background of the picture is the darker color, and then men is the lighter one. Well, no, I said it wrong. So men is the light, and the women are the dark, and then when it's like this intermediate, it's because they are on top of each other. And then you see, okay, you have certainly more men that publish a lot of articles, we know, because men are more like the, so when there are like these overachievers with 100 papers, they are most likely to be men. Whereas women tend to submit a few papers, 2, 3, etc., at higher frequency. So the difference between these two distributions we've checked is statistically significant. So these numbers, 5.7, 6.3, point to the fact that men seem to perceive that they publish more to top journals, that they submit more to top journals.
Sorry, but this is only statistics about the people who answer the survey.
Yes, yes. Later, we will go and look at the top journals, and then we'll see what comes out of that.
And also top journals was not defined the same
Yeah,
way.
yes. Yes, those are the caveats of this plot. It's perceptions, and it's what's a top journal. So that's why this is like a first, like from the survey respondents, and now we're gonna go and check it with the data. Everything fine? Can I continue?
Yes.
Again, with the caveat that when people submit to top journals, there are things that are different across disciplines. For instance, the order of authors per field is very different in mathematics, where you mostly publish in alphabetical order, than in other fields where you have this relative contribution, mostly on all of them minus mathematics, or even the negotiated order and so on. So we know also that the publication practices in different fields are different. But taking that into account, we went and wanted to check this particular data against the databases that we analyzed. So that's why now I move over to the analysis of publications, and I start talking what have we learned about the gender gap for various disciplines from the analysis of publications. And when we say various disciplines here, it's not the disciplines that the people self-reported, because we don't have access to, we couldn't analyze biology, chemistry, and computer science. So we could only analyze theoretical physics through the archive, mathematics through the CBMath database, astronomy and astrophysics through the AGS database, and chemistry only through a selection of 6 top journals. So chemistry only partial. I don't need to say why we analyze publications, because Helena said it yesterday. They are important for your academic career. Your tenure and promotion may depend on them, and they are very relevant for science policymakers, etc. So that's why I analyzed them. And we chose these ones because we could, because we had access to them, because they were open or partially open, so everything that Helena said yesterday. If we wanted to expand, which we certainly want, we would complete chemistry with the whole CAS registry, the Chemical Abstract Service. We would add biology via the bioarchive, which is the preprint service for biology similar to the archive. And we would add certainly computer science via the DBLP database, which is a database in the university in Germany that is now run by a Leibniz Institute. So certainly our analysis can and should be completed. But in what I'm saying now, I have to restrict to the data that we could analyze in these 3 years. And here are the top journals. I think this plot was shown yesterday by Helena. These are 10 journals in math that you can call top because they are quite prominent. On the left, we have mostly journals from societies, like the American Mathematical Society in France, London, and so on. Whereas in the right, we have like more topic-specific prestigious journals. And I think Helena already mentioned yesterday, we see like quite, in some of them, quite a sign of so let me explain first what we are seeing. By publication year, we are seeing the fraction of authorships by women in these journals. Okay, so it means in 1990, in this nice journal, we had 9% of all authorships that were by women. Okay, and this tendency, okay, you can say in the 70s there were fewer mathematicians, so then it's just normal. Maybe they were only 5% of all the mathematicians, then it's normal that in top journals they are so little. Fine, but 40 years later we have 3 times as many mathematicians that are women, so you should be seeing a positive trend. And rather the opposite, in the AMS journal we see a stagnation or even a decline. Invenciones Matemáticas is also quite flat. I mean, I wouldn't call this progress if we consider that the number of women mathematicians has tripled over the past 40 years. So I would expect that in absence of any bias, the number of women that publish in these top journals follows the general trend of the increased number of women mathematicians overall. If it doesn't happen, it's because two explanations. Women are not good enough mathematicians to submit and publish to top journals, which we should not accept, or that the submission and acceptance process in top journals is biased. But we lack so much data and so much insight about these practices that it's very difficult to say what the reason is for this data. I know I don't have, lunch is waiting for us, so I don't have to say everything again. These are the 6 top journals for astronomy and astrophysics, in which we know that, so if you take only the 6, you are covering a big chunk of the astronomy and astrophysics community. Here we do see a positive tendency. So we see the percentages of women authors going from something between 5 and 10% in the 70s to something close to 20% in this century, which sort of reflects and mimics the growth of the field, the growth of the percentage of women in the field. So here I would say that the top journals, yes, they are representative of the full population. So I'm more inclined to think that there is no bias or no implicit bias or subjective bias when women submit to astronomy journals. In theoretical physics, this is a disaster, pretty much having journals that have 0% of the articles of 1 year by women, and I cannot believe that there are 0% physicists submitting to them in 1 year. So it's either women think this is a very high journal, I will never get the, yes?
Didn't want to interrupt. Just before there is a question, we don't have a definition of a top journal, so just, I think Lucia has said it, but just to repeat it once more, these are selections of journals, and you can go to the website and obviously
Look at more.
Journals,
Yeah.
those that
Yeah.
you believe are very important for your
Yeah.
subfield, and check how the numbers look like there. And we did that for much more journals in mathematics and not only those
Yeah.
shown on the slide before. We did that already in a previous study as well. I mean, this is a selection to highlight some journals that are
Yeah.
on top, but obviously, as you said, for astronomy and astrophysics, those 6 shown are actually quite representative
Yeah.
of what is considered high quality.
Again, what she said is if in an ideal world, all the journals have all the representation of women that mirrors exactly the reality. Maybe some journals have more women, maybe less women, but on average they would mirror that. But then you start picking like the top from these rankings if you want, or from just asking experts to tell you what are the good journals. And then on those, the fraction of women is significantly less than on the reality, no? The number of people that actually publish in physics. Then you see a hint for a bias.
Do you have any idea how many papers are submitted by women in comparison to men? Maybe they submit a lot less than men do.
Yeah, we don't know that because publishers will never give you this data. So that's my conclusion of all this is that we need transparency into submission rates. If we cannot get them from the publishers, then we should by all means analyze grant proposals because those are public and those go to public agencies, and we should ask for the data from grant proposals. And when this has been done, the results is that women submit already less, maybe because of discouragement, and when they submit less, there are also granted grants less. So it's in both of these stages, at least in grants. I cannot say anything about journals because I don't have the data, but I suspect those 2 aspects are confounding here, and is that you lack the motivation or the support or whatever to first submit, and then when your paper or grant is there, you also face some bias from the editorial board. Because studies have been shown that both female and male reviewers are harsher with women's papers. Both. So I'm not saying that it's because the editorial board is just men. I'm saying because in general there is the subconscious bias that a paper by a woman is intrinsically less or she has to prove more.
Talk about submitting without any name.
Yes, blind review and blind submission, of course, yes.
Can we keep and hold the question for the end of the talk? Thank you.
Chemistry is a good surprise. Mark tells us it's not surprising, it's noteworthy, because chemistry also follows more or less the trends of astronomy and astrophysics. So if you were to tell me what have I learned about the gender gap through the analysis of top journals, is that astrophysics and chemistry don't seem to show a gender gap, whereas mathematics and physics do show a gender gap. And the applied field seems to have larger female representation than the pure fields. This is seen here in the journals that are applied here have a better, so for instance, the Siam Journal of Mathematics, have better trends than the pure fields. But mostly, what I learned from this is that we need more transparent data on this process, because biases that exist are unknown and immeasurable. Let me continue. Now we went from these top journals to the whole database. And the first thing we did was to go to every cohort, so every year, there are new authors that start publishing in the database. No? The first paper by Marie-Françoise Roy was in this year, so in some year, and then she is in the cohort of that year. And then we compute per year how many of these authors that start publishing this year, which is a proxy for your first paper, is a proxy for your PhD stage, sort of. So how many people enter the field per year? And that percentage of women has been steadily increasing from 10% to 30%. That's what I meant, that we have tripled the number of women entering mathematics over the past 30 years. So that's why this is the plot that doesn't correlate with this, right? Because if you have 30% women today in mathematics, you cannot expect that only 8% of them publish in top journals. Okay, you can say they are too young today, fine, but then why are the numbers so stagnant since 30 years ago, see? So this is what we get from this analysis compared with the top journals. I see a gender gap in the publications in top journals. So I see a bias when it comes to entering really the high ranks of your profession. Maybe the glass ceiling effects, all those things. In astronomy and astrophysics, though, we see again the same trend from 10% in the 70s to 25–30% today. By the way, here is the number, absolute numbers, so you can see that mathematics is a field in which approximately 10,000 people enter new every day, whereas astronomy is a field that is about half the size of mathematics today. But the trend of astrophysics is mimicked in the top journals of astrophysics. So this is why I say in astronomy and astrophysics, I don't see the gender gap in when it comes to the publications in top journals. And then theoretical physics, 8% to 20%. Again, I see the bias, or I see a gender gap, because it doesn't correlate with these flat lines here. Moving on, we can try to think of an explanation. What is different in mathematics from astronomy and from theoretical physics? Certainly, the size of the teams. Mathematics has been, so what I'm showing here is per year, what's the percentage of papers that have one author, two authors, 3 or 4 plus, and then I look at the years. So this is mathematics on the top. You see that in the 70s, 80% of the mathematics papers had one author, 19% had 2, and then the few percent had 3 or more. So it's a field in which you write your paper, and now in these years, now it has become a field in which you write your paper, you and your friend. Maybe you, your friend, and a third friend. But this is it. It's big. It's a small team community. So ties are very important. Ties to your doctoral advisor, ties to your very small university team, and it's you and your friends, so to speak. Now we look at astronomy and astrophysics. In the 70s, only 30% of all the astronomy and astrophysics papers were written by one person. We know that in astronomy, it's you and your, I don't know, your other 500 friends. So it's very different. And what does this foster? Maybe this fosters less fear to be in collaborations, less fear to be out there and publish, more inclusivity because the teams are big. I don't know. It could be an explanation. But certainly when things are closed and gatewayed and there are few people in power, this is disadvantageous for women. So opening the field, opening the collaborations, may be positive to close the gender gap. But of course, I cannot say here, let's all mathematicians publish papers with 100 people. But you know what the trend is. The trend is maybe more collaboration, more diversity, more inclusivity helps close the gender gap. Doesn't go that well with theoretical physics, because theoretical physics is sort of in between maths and astrophysics. So there are certainly big collaborations in theoretical physics, but not as large as the astronomy ones. So what can we say? This is as bad as mathematics, so but it's still a bit more collaborative field than mathematics. So yeah, we need to see. I cannot give completely for sure answers. But because the time is ticking, let's go to my summary. This was a big project. This was a very complicated project, and this is, of course, a very serious and hard problem that is very difficult to solve with our just little insights on it. And also when it was designed, it was designed in this way, that the survey answers some questions, the task 2 answers another questions, and it has been difficult to find consistent answers and trends from the project, because what people perceive and what people self-report, and also the way the survey has been designed with this snowball sampling, may not be the full reality. It's not, it cannot be. But also the analysis of the publication databases is not the full reality. That's just the manifestation of people that publish a lot. But we know that there are many scientists, physicists, mathematicians, biologists, etc., whose main focus is not on publishing, maybe it's on teaching. So they are also not reflected in our task 2. Therefore, it's just normal and to be expected that these results are difficult to reconcile, and none of the 2 pictures that we get from the survey and from the task 2, none of them are complete. All of them are incomplete, and this is it because reality is very difficult to model. However, there are some things that we can say, because if not, that would be very bad. So from the survey, we can say, for instance, that there is no perception of inequity across fields regarding submission to top journals. But from the analysis of publications, we see a mismatch between the percentage of total female authors and female authors in top journals. So we know from the data of the analysis of publications that there is some bias in publication to top journals, bias that is not seen in the self-reported perceptions of the people. So maybe a bit of continuation of the project could be to try and reconcile these 2 views of the problem. Again, I say it again, that the differences in perceptions that were extracted from the survey do not necessarily align with the results from the publication analysis. But anyways, from the point of view of the scientific output, so from the point of view of the publications, astronomy and astrophysics, and also chemistry, present the smallest gender gap of all 3 analyzed sources. So that we can say, that we've learned from the gender gap across disciplines, that there is a larger gender gap in mathematics and in theoretical physics than in astronomy and astrophysics regarding the publications. And maybe a potential explanation for it is that astronomy and astrophysics is a more collaborative and inclusive field, if you want, like with larger teams, and maybe that plays an important role into making the coming of women easier. I'm going to leave some 10 minutes for questions, comments, and feedback, and I thank you very much for your time and attention.
Thank you, Lucia. Yes.